Now in this lesson, we're going to talk about a method called partial fractions. And typically when we're dealing with rational expressions, we usually want to combine those rational expressions together in one fraction by finding a common denominator and then adding them or subtracting them together. Now, with partial fractions, we're doing the reverse. So a lot of times when we want to integrate something that contains a rational fraction, a lot of times it's easier to use the reverse process and express the rational fraction as the sum or difference of simpler fractions. And then when we split it up into simpler fractions, usually that's a lot easier to handle when we're integrating. So basically, you want to think of partial fractions as the reverse of adding and subtracting rational expressions. So sometimes you need to use long division, sometimes you need to use factoring, but basically what we want to do is break a rational expression down to its simpler fractions. So in this first example, this is a nice easy one to get started with. What I suggest is if you notice your rational expression that you're trying to integrate has a degree on the top that's larger than the bottom, you want to try to break this fraction up into simpler parts by doing long division. So we're going to take x squared plus 3x plus 5 and divide by x plus 1. Now, our answer would be x plus 2. Once we walk through the procedure, we're going to get x plus 2 with the remainder of 3. So I'm going to rewrite this expression as x plus 2 plus 3 over x plus 1. So I'm just rewriting this original rational expression in terms of its quotient and remainder. So now this is a bit easier to integrate. If I integrate this, I can just use the power rule for integration. That will be x squared over 2 plus, this will give me 2x. And this will give me 3 natural log of x plus 1. And then, of course, my plus constant. Now, in our second example, we're going to look at partial fractions with non-repeated linear factors. So here's what we want to integrate. We have 3x plus 2 over x to the third minus x squared minus 2x. Now, in this case here, because the degree of the numerator is less than the degree of the denominator, we do not have to worry about using long division to break it down. So the next step after we look at that is we want to take the denominator and factor it as much as we possibly can into linear factors. So when we factor this, we get 3 linear factors and none of them repeat. That's important that we pay attention to that because there's a different process if any of the factors repeat. So since none of these repeat and I have 3 factors in this denominator, we're going to split this up into 3 fractions. And each of these smaller fractions is going to have each of these factors in the denominator. Then we're going to write a, b, and c respectively across the top, and we're going to set it equal to our original rational expression. So we want to rewrite an expression so that we have 3 simpler fractions that's equivalent to this original fraction. All right, now if we were looking for a common denominator, what I would do is I would multiply the top and the bottom of this fraction here by x minus 2 and x plus 1, which means in the numerator I would have x minus 2 times x plus 1 times a. For this fraction here, if I were to find a common denominator, I would multiply the top and the bottom by x and x plus 1, which means in the numerator, I would have b times x plus 1. Then for this last fraction here, to find a common denominator, I would multiply the top and the bottom by x and x minus 2. So in the numerator, I would have c times x minus 2. So that would be what I have in the numerator and create a common denominator. And that should be equivalent to 3x plus 2. So I'm going to set up that equation to 3x plus 2. Once I clean this up and I expand everything and get rid of the parentheses, what I would have is ax squared minus ax minus 2a plus bx squared plus bx plus cx squared minus 2xc, and that should all be equivalent to 3x plus 2. So now you want to try to look at your like terms, and I color coordinated it here. I have an x squared here, an x squared here, and an x squared here. So if I were to combine these, I would get a plus b plus c x squared. Now, because there's no x squared here, when I combine those, I want it to be 0. So I want a plus b plus c to be equivalent to 0, so that I get a term that's 0x squared. So I have this, a plus b plus c is equal to 0. Now look at the x's, those I put in green. So I have a minus ax, I have a bx, and I have a minus c times 2x. I want, when I add all of those, for that to be equivalent to 3x, which means my coefficients minus a plus b minus 2c should be equivalent to 3. So then I set this equation up here. Lastly, I'm looking at my constant. Now in all of these, the only constant I have is this minus 2a. So minus 2a should be equivalent to 2. So that's what I have here. So that means I know that a is going to be negative 1. And then I go back and substitute and use my knowledge of solving a system of linear equations to find the rest of my values for a, b, and c. Once I find my a, b, and c, I can go back up here and substitute it, and I'll get an expression that's the same or equivalent to 3x plus 2 over x times x minus 2x plus 1, but broken down into simpler fractions. And then I can rewrite that down here. So a is negative 1. So I'm going to put negative 1 here. So I get negative 1 over x. That's this here. I get that b is 4/3. So I put 4/3 here. 4/3 x minus 2. And then minus c is negative 1/3. So I put 1/3 up here, negative 1/3. So I get a negative 1/3 x plus 1 here. Now this is much easier to integrate, and I'm using the natural logs. I'm going to have minus the natural log of x plus 4/3 the natural log of x minus 2 minus 1/3 the natural log of x plus 1 plus our constant. In this next example, we have to divide and use partial fractions. So we need to evaluate the integral of x squared plus 3x plus 1 over x squared minus 4. Now I notice that I can use long division on this, so that's what I want to start off with. So when I take x squared plus 3x plus 1 and I divide by x squared minus 4, it goes in one time with the remainder of 3x plus 5. So the first thing I'm going to do is rewrite this integral as the integral of 1 plus 3x plus 5 over x squared minus 4. Now I can split this up into separate integrals. This I can integrate directly, and for this integral, I have to actually now use partial fractions on this. So the first thing I want to do when I start my partial fractions procedure is I want to factor the denominator. So when I factor that, I get x minus 2 and x plus 2. Now, as you can see, I have two linear factors and they don't repeat. And it's important to point out that they don't repeat because if they did repeat, there's a different procedure for that. So this means since they don't repeat and I have two factors, I'm going to have two fractions when I split it up. So in the denominator of the first fraction, I'm going to put x minus 2. And in the denominator of the second fraction, I'm going to put x plus 2. And then in the numerators, I'm going to put in my a and b, and that's what we're trying to solve for so that we know how to break this up. So now if I imagine that I'm trying to combine these and find a common denominator, I would take and multiply x plus 2 by the top and the bottom of this first fraction, which means I would have in the numerator a times x plus 2. For the second fraction, if I was trying to find a common denominator, I would multiply the top and the bottom by x minus 2, which means in the numerator I would have b times x minus 2. And we want all of that across the top to be equivalent to 3x plus 5. So now when I expand this, I get ax plus 2a plus bx minus 2b is equal to 3x plus 5. Now, if I look at my x terms, I have ax and a bx. So I want a plus b to be equivalent to 3. So here's where I get my first equation. For my constant, I want my constants to add to 5. My constants are 2a and a minus 2b. So I want 2a minus 2b to give me 5. Now, when I solve that, I get that a is 11 over 4 and b is 1/4. So I can go back in and substitute for my a and b now. So this second integral we rewrote as 11/4 over x minus 2 plus 1/4 over x plus 2. And so when I integrate that, I get 11 over 4 natural log of x minus 2 plus 1/4 the natural log of x plus 2 plus my constant. And then we don't want to forget about this first integral, the 1 dx. And so when I integrate that, I would add x from that first integral. So my final answer is going to be 11/4 natural log of x minus 2 plus 1/4 natural log of x plus 2 plus x. You make sure you add that in, and then plus your constant. Sometimes we need to use partial fractions after a substitution. And so here's an example of that. We're going to integrate cosine x over sine squared x minus sine x. We're going to do a substitution and let u be sine x. So when I take the derivative of u, I get cosine x dx. So I'm going to replace cosine x dx with du. So cosine x and dx is going to now be replaced with du. Everywhere I see a sign, I'm going to replace it with u. So here's u and here's u. So I have a u times a u minus 1. That's this down here. So now we have it in a form that we can use partial fractions. So I am going to break this up into two fractions because I have two non-repeating linear factors. So in one fraction, I'm going to let u be in the denominator. In the other fraction, I'm going to let u minus 1 be in the denominator. And so I'm going to write a over u plus b over u minus 1 is equal to 1 over u times u minus 1. So when I go to actually try to combine these, I would multiply the top and the bottom by u minus 1 with the first fraction. So in the numerator of the first fraction, I would have a times u minus a. In the second fraction, I would want to multiply the top and the bottom by u. So I would have b times u in the denominator. And so when I add those up, it should be equal to 1. And when I solve for a and b, I get that a needs to be equal to negative b, so they got to be the same value but opposite signs. And then you'll find that a is negative 1 when you solve this. So that means a is negative 1, which means b is positive 1. When I go back and replace that, I get a negative 1 over u plus positive 1 over u minus 1. And I'm going to integrate these two fractions. And so now I have minus the natural log of u plus the natural log of u minus 1 plus the constant. And then I'm going to go back and resubstitute that u is sine x. So everywhere I see a u, I'm going to replace it with sine x. So here is my final answer. So here is an example of where we're going to use the method partial fractions where we have repeated linear factors. So we're going to evaluate this integral of x minus 2 over 2x minus 1 quantity squared times x minus 1. First thing I notice is I don't need to use long division to start off with because the degree of the numerator is smaller than the degree of the denominator. So the next step then is to factor the denominator. And this one's pretty much already factored for us. We have 2x minus 1 times 2x minus 1 because it's squared, and then x minus 1. So we have 3 factors in the denominator. And 2 of them are the same, so we have repeated linear factors. So when you rewrite this using partial fractions, you have to have a fraction with a denominator for all the powers leading up to and including the power that's given. So I have to have a fraction with just 2x minus 1, and I also have to have a fraction with 2x minus 1 squared. If this was 2x minus 1 to the third, then I would also have to have a fraction of 2x minus 1 to the third in the denominator. So because this 2x minus 1 is squared, I'm going to have 2 fractions, one where it's squared and one where it's to the first power. So here's where it's squared, here's where it's to the first power, and then of course I can't forget this other factor here of x minus 1. And then I'm going to set it up with my a, b, and c on top. Then I'm going to go through the process of finding a, b, and c by going through the process in which I would if I was trying to find a common denominator. So for this first fraction here, if I was trying to find a common denominator, I would multiply the top and the bottom by x minus 1. So I would have a times x minus 1. For the second fraction, if I'm trying to find a common denominator, I would multiply the top and the bottom by 2x minus 1 and x minus 1. So that would leave me with b times 2x minus 1 times x minus 1. Then for this last fraction, if I was trying to find a common denominator, I would multiply the top and the bottom by 2x minus 1, 2x minus 1. So that leaves me with c times 2x minus 1 times 2x minus 1. And all of that, when I add it up, has to be equivalent to the numerator of our original expression, which is x minus 2. Now, once I clear the parentheses and I combine like terms, I want to come up with a system of equations so that I can identify the values for a, b, and c. So let's first look at all the x squared terms. That I did in blue. So here's an x squared term. Here's an x squared term. So because I don't have an x squared term here, I want my coefficients to add to be 0. So I want 2b and I want 4c to be equal to 0. So that's where I get this from. Now let's look at our x terms, which is the green. So I have an ax here, a minus 3bx here, and a minus 4cx here. So I want all of those coefficients to add up to 1. So that gives me an a from this, a minus 3b from this, and a minus 4c. I want that to add to give me 1. And then I want all my constants to add up to give me a negative 2. So when I look at my constant stacks in red, I've got a negative a, I've got a positive b, and I've got a positive c. So those coefficients need to add up to be negative 2. So here's my third equation. So I use systems of equations to solve for a, b, and c. So I get that a is 3, b is 2, and c is negative 1. So I go ahead and substitute those in for a, b, and c right here. And so what I get when I rewrite this is I get 3 over 2x minus 1 squared, because that's the 2x minus 1 times 2x minus 1. On the second integral, I have 2, which is my b over 2x minus 1. So I have my b, which is 2 over 2x minus 1 plus, and my third integral, I get the c is negative 1. So I have negative 1 over x minus 1. And now we can go ahead and integrate. So I'm going to let u be 2x minus 1. So du is 2 dx, which means I can replace dx with 1/2 to u. So when I do my substitution, I'm going to get 3/2 u to the negative 2. This 2 comes up as a negative 2 to make it easier to use the power rule. And then I have this 3 here, which is this 3 here, and then the 1/2 du that replaces the dx, so that's where this 2 comes from. Now, when I replace u here, I have 2 over u, and then since I have a 1/2 du, this 2 and the 1/2 cancel, and I'm left with just du over u. This I can directly integrate. So that's going to be minus the natural log of x minus 1 and then plus our constant. Now when I integrate these two, I get 3/2 u to the negative 1 over negative 1. That's this one here. When I integrate this, that gives me the natural log of u. This I just carry down. And then when I go back and substitute for u, I get negative 3 over 2 times 2x minus 1 plus the natural log of 2x minus 1 when I substitute the u here. And then I have this that I just carried down that I integrated directly. And so this is my final answer. Now, if you're trying to integrate something and you want to use partial fractions and you go to factor the denominator and you can't factor it in linear factors over the reals. So here's our example of that. So we have the integral of 2x minus 3 over x to the third plus x. When I factor this, I have x times x squared plus 1. This cannot be factored over the reals. So if I want to use partial fractions, I'm going to have to set up my fractions differently. So when we set our fractions, if we have a quadratic denominator, then in the numerator, you're going to set it up, rather than a constant, you're going to set it up as linear. So you're going to have ax plus b. Now, that's just for your quadratic denominators. So when I set it up where x is in the denominator, that's just going to be a constant because this is a linear factor. So we're going to set this up as ax plus b over x squared plus 1. And again, this is set up not as a constant, but as a linear factor because we have x squared plus 1, a quadratic denominator, plus c over x is equal to 2x minus 3 over x times x squared plus 1, which is our original denominator before we split it up. Another thing I wanted to point out is we don't have to worry about long division to start this off with because the degree in the numerator is less than the degree in the denominator. So we don't have to worry about starting off with long division. So we're going to jump directly into partial fractions. And in this example, we're going to do an irreducible quadratic factor. So if I were from here to go ahead and create a common denominator, I would want to multiply this first fraction on the top and the bottom by x. So I would have ax plus b times x, which would be ax squared plus bx. Then I would want to multiply this fraction here with the c over x. I want to multiply that on the top and the bottom with x squared plus 1. So on the top, I'm going to have c times x squared plus 1, which would be cx squared plus c. And that should give me my numerator, 2x minus 3. So I set all of that equal to 2x minus 3. And then what we're going to do is we solve for a, b, and c here. I'll let you work out those intermediate steps now that we've gone through a couple of examples. But once we find our a, b, and c, then we plug back in up here and we can integrate. So in this case, we get that a is 3, c is negative 3, and b is 2. So I'm going to plug those values in up here. So when I split up my fraction, 2x minus 3 over x to the third plus x, I'm going to get 3x plus 2 over x squared plus 1. Here's my a, x plus b. And then here's my c over x. I get a minus 3 over x. So I'm going to break that up into my two integrals, and then I'm going to integrate these. So I'm going to use u substitution from here. I'm going to let u be x squared plus 1. So du is going to be 2x dx, which means I can substitute x dx for 1/2 du. So this down here becomes u, and I'm left with 3/2 du, because the 1/2 is going to come from this 2 here when I replace x dx with 1/2 du. So this is what I get here, the integral of 3/2 1 over u du. For this second interval, we actually have a direct formula for this. When I integrate 2 over x squared plus 1, that's actually 2 times inverse tangent. If I pull that 2 out in front of this integral, you'll see, and you look up on your table of integrals or in your formula sheet, you'll see that the integral of 1 over x squared plus 1 is inverse tangent. So we have a direct formula for that. And then, of course, we know this one. This is minus 3 natural log of x and plus my constant. So I've integrated these two here. I still have to integrate this because all I've done at this point is I've done my u substitution. So when I integrate this, I get 3/2 natural log of u, and u we said was x squared plus 1. And then everything else I carry down. So this is my final answer. Here we have another example of using the partial fractions method with an irreducible quadratic factor. But in this example, it gets more complicated, and we'll see why here. So we have to integrate dx over x to the third minus 8. And so when we factor the denominator, we get x minus 2 times x squared plus 2x plus 4. Now, this is a linear factor. This is not a linear factor, and I cannot factor this anymore over the reals. So when we create our fractions, I'm going to have two fractions here, one for this denominator and one for this. So for this denominator, since it's a linear factor, I'm going to have a, just my constant a, over x minus 2. And then for the irreducible quadratic factor, my numerator needs to be linear. So this is going to be bx plus c. And so this is all going to be equivalent to 1 over x minus 2 times x squared plus 2x plus 4. Now, when I go to try to determine what my a, b, and c values are, to create a common denominator, I would have to take a times x squared plus 2x plus 4, and that would give me this. To create my common denominator here, I need to multiply the top and the bottom by x minus 2, so I would have bx plus c times x minus 2, and that would give me all this here. And so all of this would be in the numerator, so that needs to be equal to 1. Now, I'll let you guys work out the intermediate steps, but what ends up happening, you get a is 1/12, b is negative 1/12, and c is negative 1/3. So I'm going to replace a with 1/12. That goes here, 1/12 over x minus 2 plus b is negative 1/12 x, so that goes here, x is here. And then c is negative 1/3, so that goes here. So to make things easier, I split up this integral into two pieces. I've got 1/12 times the integral of 1 over x minus 2. That's this piece here. For this second integral, when I split it into two, I'm going to pull out a negative 1/12, so that's going to come out here. And then what happens is I'm left with x plus 4 when I factor out a negative 1/12 because I create a common denominator with this negative 1/3. I make that negative 4/12. And so when I factor out a negative 12, that leaves me with x plus 4. So x plus 4 is in the numerator, and then I still have the x squared plus 2x plus 4 in the denominator. This integral right here is ready to go. It's ready to be integrated. But this one here, as you look at it right now, I can't use u substitution. There is no formula for this. And also, I can't use partial fractions on this again, a second time, because this is irreducible. So a neat trick that you can use so that you can use u substitution, you can complete the square on the x squared plus 2x plus 4. So when I complete the square, I am going to add in something here to make it a perfect square. But whatever I add in here, I have to do the opposite. So I'm like adding in 0. So to complete the square, I take half the 2 and square it. So that gives me 1. So I want to make sure that I don't really add anything in. So I'm going to subtract a 1 over here. So I'm just rearranging it. So this part here, I can rewrite it as x plus 1 squared, because this is the perfect square. And then 4 minus 1 is 3. So I rewrote this expression right here as x plus 1 squared plus 3. So I'm going to carry this down. This, I'm going to rewrite it using the complete the square method. So I have minus 1/12, the integral of x plus 4, and then in parentheses, I have x plus 1 squared plus 3. Now we have this set up where we can use u substitution. We're going to let u be x plus 1, so du is going to be dx. And if I rearrange this u equals to x plus 1, I also have that x is u minus 1. So when I make those substitutions, I'm going to get negative 1/2 times the integral of u plus 3 over u squared plus 3. Again, I'm just bringing this down. Then I'm splitting this up into 2 separate integrals. And I'm going to have to use u substitution again on this middle integral. So here's my u substitution for that middle integral. So this time I'm using v for my substitution so I don't get my u's mixed up. So this first integral keeps getting carried down because this is ready to go. So I have 1/12 the integral of dx over x minus 2. When I do my second substitution on this integral, I have minus 1/12 times 1/2 dv over v. And this one here, I'm just carrying down for right now. I have 1/12 times the integral of 3 over u squared plus 3. Now, let's finish this up. Woo, this one was a long one. This one, when we integrate, it's ready to go. We have 1/12 natural log of x minus 2. This one, when I integrate this, I get 1 over 24 with the minus in front because I have this 1/12 times this 1/2. That gives me 1 over 24. And this is the natural log of v goes in here. But when I back substitute a couple times, I get x plus 1 squared plus 3. V is u squared plus 3. So when I replace this with u squared plus 3, and we said that u was x plus 1, so we end up with x plus 1 squared plus 3. For this last integral, we have 1/12 times the integral of 3 over u squared plus 3 du. And if you look on your reference tables at integral formula number 16, that's why I marked that here, you'll be able to use that formula to do this last integral here. And then you have your plus c. Whew, that was a long one. Very involved. We had a partial fraction, we had a complete the square, and then we had a u substitution twice. So we're going to find the volume of the solid of revolution obtained by revolving the region enclosed by the graph of, and then we have the function x squared over x squared plus 1 squared. And we're going to enclose it with the x-axis over the interval from 0 to 1, and we're going to spin it about the y-axis. So we're going to spin it this way. It's going to create a shape that looks kind of like a cylinder with a dip in it. Sorry, I'm not the best artist. I think using the shell method here is going to be the easiest. So we're going to integrate from 0 to 1. That's the interval that we're interested in. Using the shell method, we have to take 2 times pi times the radius times the height. So the height is going to be the function. And then we're going to multiply it by the radius, which is x. And we're doing this all over from 0 to 1. Now, when we use partial fractions here, not only do we have an irreducible quadratic factor, this x squared plus 1, but we also have a repeating factor. So when we set up our partial fractions, we have to have 2 fractions, one with x squared plus 1 raised to the first, and one with x squared plus 1 raised to the second. So here's to the first power, here's to the second power. Because our factors are not linear, and they're quadratic, we need to set up our numerators as linear. So in our numerators, we're going to have ax plus b, and then in the second numerator, we're going to have cx plus d. And these 2 fractions, when we add them up, should be equal to our original fraction, which is x to the third over x squared plus 1 squared. Now I'm going to let you guys find the values for A, B, C, and D, and you guys can do those intermediate steps. But what you should get is that A is 1, B is 0, C is -1, and D is 0. So when we substitute those values back in for these fractions, and we split it up into 2 integrals, I have 2 pi times the integral from 0 to 1 of x over x squared plus 1. A is 1, so that gives me a 1x, plus b is 0. So I just have 1x up here. Now, since c is negative, this is going to become a minus 2 pi. And I'm going to have x plus 0, which is just x in the numerator, all over x squared plus 1 quantity squared. Now we can continue evaluating these integrals by making a substitution. And it just so happens that these 2 substitutions are the same, so that makes it a little bit easier. For both of these, we're going to let u be x squared plus 1. So du is going to be 2x dx, which means I can replace x dx with 1/2 du. So when I replace this x dx with 1/2 du, this 2 and this 2 disappear, and I'm left with just pi. Same thing over here. When I replace the x dx with 1/2 du, the 1/2 and this 2 disappear. They divide out, and I'm left with 1 pi, so that gives me this. I also need to remember to change my limits since I'm changing variables, and this is a definite integral. I have to make sure that I adjust my limits appropriately. So I got to change when x is 0, I'm going to change that to u is 1. When x is 1, I'm going to change that to u is 2. So on both integrals, my limits are going to be from 1 to 2. Now, when I substitute u on this integral, in the denominator, I have u squared because this is squared here. So now this is set up to integrate. So when I integrate this, I have, like I said before, the 1/2 times the 2, I'm left with just a pi here. And when I integrate 1 over u, that leaves me with natural log of u. Same thing here. When I take 1/2 times this 2, that just leaves me with the pi. And then when I integrate 1 over u squared, that gives me negative u to the -1. And don't forget when you're evaluating this, that makes this a double negative. So watch those two negatives there. Now I have to evaluate that on the interval from 1 to 2. And when I do that, I get my final answer is pi times the natural log of 2 minus pi over 2.